Okay, so today we're going to be talking about all about resonance. So I think resonance is probably the first real subject that comes up in OChem 1 that is usually just really tricky for people. I think that's the easiest thing to get stumped on a little bit because I think all the beginning lectures that you have in OChem would really be kind of review from things from Gen Chem, but I feel like Resonance was really the first, at least for me, the first thing that was completely new. So essentially, Resonance is just the transfer of valence electrons from one bond to another, whether it be a lone pair or a pi bond, which is a double bond. So what does that mean? So let's just draw out a little structure here. And okay, so we have a oxygen here, double bonded, and at the other end, we have just a single bond to an oxygen. So this we know would have two lone pairs, so four valence electrons is sitting here. But this one doesn't have a double pair or a pi bond. I mean, so this would have, if you count it up, this would be uh, six electrons or three lone pairs. So that would give it a negative charge, since we know oxygen wants to have six valence electrons, but this here would have seven. So if you can, I mean, as you know, the double bond or the single bond, I mean, sorry, the covalent bond here would be sharing one valence electron between oxygen and this carbon here. So this would have one, two, three, four, five, six from the lone pairs plus one from the covalent bond. So oxygen wants six, but we really have seven. So if you think of it just as 6 minus 7, since electrons are negative, this would have a negative 1 charge. That's what gives it a negative charge here. So we have the ketone, which is just the fancy word of saying a carbon oxygen double bond has 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4 from the lone pairs, 6 from the covalent bond. So 6 minus 6, we get 0 valence. That's why it has no negative charge. So just a little background in case you were wondering why that has the negative charge. So what can happen here? And I thought, at least for me, this was kind of a wild thing to wrap my head around. When this molecule is existing, it can shift between two, we call it resonance structures, but you can think of it as just forms of the molecule. So essentially, double bonds like this could turn into, could the double bond here, so this, that was a bad way of drawing it, to be honest. So the double bond can shift and move to a singular carbon to give it a lone pair. So what does that mean exactly? So this this group right here, this lone pair, could move, since oxygen doesn't really want to have a negative charge. It is electronegative, but it never really wants to just have a negative charge. It can shift, placing the lone pair into a double bond. So we'll draw that form in a second. So you might be thinking, well, how can, if we look at this carbon here, how can we have double bond, another double bond, and a fifth covalent bond? Since we know we can't have five bonds to one carbon. That's like the most essential rule of OChem. You can't break that. So this double bond here, the valence electrons will shift, get out of the way to make room for that double bond, and go to the oxygen. So what exactly will that look like in the resonance structure? So let's draw that out. So we have, oh, I'm sorry, that was wrong. So we can have a structure that looks something like this. So now the double bond oxygen is now a single bond, and the double bond, I don't know what that was. The single bond oxygen will now have a double bond with no net charge. So essentially, the charge has just shifted from one oxygen to the next. And in order to facilitate that, the lone pairs had to shift here and go from this oxygen to add to the covalent bond to make it a pi bond, to add to the pi bond. So essentially, These molecules are, hold on, let me draw this. If we think of it, if you had a test question that was just saying what would be the primary, my bad, this is my first time using this. If you had a test question asking us what exactly would be, sorry, I'm just getting everything out of the way. If you had a test question asking you what would be the primary resonance structure of this molecule, it would be what I just drew. Because we could hypothetically move the, see, I'm going to draw this here. So we could hypothetically have other resonance structures because there could be positive charges. So we could hypothetically make this lone pair, or not lone pair, I'm sorry. We could make this double bond I'm circling around become a lone pair on the carbon. So let's just draw that out. So just for FYI, this would not be a correct answer, but I'm just doing hypothetically. You could be thinking, well, if a double bond, if a pi bond can become a lone pair, can it also go to carbons? So let's kind of just draw why that really wouldn't happen. So we have that. Then now we have two oxygens with double, or actually this would be a plus charge because it's missing a valence electron, and we could put this here. So that would not be there. It would be like this and giving us a negative charge on the carbon. So this really wouldn't happen if you had a test question and you had to draw the primary resonance structure. This would not be the correct answer, mainly because if we think of it, anytime we have I might just write this down because it's kind of a big thing. Ions, or just not really ions, but charges. When we think of OChem, any sort of charge on a molecule brings instability. These are somewhat sources of instability that can react. Later on, I will go into things such as SN1, SN2, and we know that, we know that having the negative charges and positive charges will bring in unwanted reactions. So we really don't want that, and it brings instability. So we know that these we don't want to have 1, 2, 3. We don't want to have all these charges here on this molecule when we really could just have, like, this has one charge as in one source of negative charge. This one has 1, 2, it has 2 negative charges and 1 positive charge. Yes, that will somewhat balance out, but it's still unnecessary. Why would we want this molecule to have all these ions, all these sources of charge, when we really don't need that? We only should have 1 negative charge anywhere. If we just drawing unnecessary charges is just it's just very unnecessary. Just long story short. So let's talk a little bit about, I probably should have started with this, but what are localized and what are delocalized lone pairs? So I think the easiest way to draw this out is, let's do nitrogen, because I think that is an easy element to show in this case. So we have nitrogen, and it has a double bond, a single bond, and a lone pair. So it is, as we know, nitrogen wants 5 valence. Excuse my handwriting. 5 valence electrons. So we have 1, 2, 3, 4, 5 from all that. So it has 5. It doesn't have a charge. We're doing good. And now on this, we will have let's draw another double bond, and let's have a nitrogen here. And let's have hydrogen, but and it will also have a lone pair. So this lone pair here, I'm going to circle this lone pair on that nitrogen, that is a that is localized lone pair. So let's just kind of And you might be wondering, why is this localized? So essentially, this nitrogen here, let's just kind of, I'm just going to draw it out in a more simplified way. So we don't need to draw everything else. So this nitrogen here has a double bond. So this double bond can move, it can shift, it can gain. No, it can gain. This double bond can move from here, or it could go. Let's reverse that. It could go here. So it already has. If you think about it, localized. I'm just gonna back up just a little bit. Localized means it's not going anywhere. This lone pair on this nitrogen is never going to move. It's never going to participate in resonance. It's always going to stay right here on this nitrogen. So the reason why this isn't going to move is because this nitrogen already has a source of resonance from this pi bond, this double bond here. So this could go here and bring a double bond there, or it can bring a lone pair there, sorry. Or it could move here and give us a new source of lone pairs, but it's never going to go anywhere else. This is going to sit here, okay? So this could shift here, this can shift here, but this lone pair has no reason to shift. So let's draw this out. So if it was like, if it was like this, and say this goes right here, let's draw how that would look. So it would look something like, so that carbon, I'm just gonna actually do that. So let's just draw this. We know this is carbon, that's just a C just to make it simple. This carbon now has a negative charge because it's a lone pair, but this lone pair here, it still isn't going anywhere. This can't replace that double bond, because if we think about it, this carbon already has a lone pair. So if hypothetically, this isn't how this actually works, but hypothetically speaking, if we had this here, this already has a lone pair, it doesn't want to move. If we added on a double bond, a pi bond from this lone pair, this carbon here would already have a lone pair. So it would have, how much would that be? Like 5 or 6 valence electrons, and it would have 7 or 6 valence electrons, which we know is never going to happen to a carbon. A carbon's never going to take in that many. So if it did shift like this, let's just kind of draw this out hypothetically. This would be the resonance structure. This would go here, giving us a negative charge on the carbon. Let's just try one more time. This would have a negative charge here, and then this nitrogen would just now gain a positive charge. And this lone pair, it's sitting right where it wants to be. It has nowhere to be. It's happy right there. So now let's draw. So that's a localized. So let's explain delocalized lone pair. So delocalized, if localized, you kind of think of it, it's staying at home, it's local. Delocalized, it means it's moving. So how does that make sense? Like, well, how does that work? So this lone pair can move because this double bond right here could shift and add its valence electrons to the singular carbon right here. It could add, giving us a negative charge on the carbon. Oh, I kind of did it wrong. So let's just kind of draw this a more simplified way. It's just, so this now would have a negative charge on this carbon. So this lone pair, since removing this shared, so we know a double bond, as we know, it's 2 valence electrons. So each carbon gets 1 valence electron. So if we remove 1 valence electron from this carbon here, right here, we know that it would now have a positive charge because it just its double bond just left it. It went to go to that carbon, so it's all alone. It has a positive charge. So in order to replace that, in order to kind of mitigate or like just remove this positive charge, the lone pair says, let me join, let me help you out, I'm gonna donate, I'm gonna give you a lone pair. So it goes like this, it donates. So now there would be a double bond between here, this nitrogen here, as we saw, and the carbon that just lost its the carbon that just lost its pi bond. It just got replaced by the lone pair here. Nitrogen said, "Let me help you out. I'm gonna give you my lone pairs, we're gonna remove this positive charge. So now we don't have unnecessary charge. But as we know, since this nitrogen, we want four, or no, we want 5 valence electrons, but it only has 1, 2, 3, 4. So this would now have a positive charge. But it is easier for just stability wise. A nitrogen would rather take on the positive charge than a carbon, I believe. But correct me if I'm wrong. I am still a undergrad student. I don't know everything. So I hope that kind of explains some things, helped you out, because I know resonance is probably the first, as I said earlier, it's the first really tough um, unit, I'd say, in OCHEM. It's the first really tough conceptual thing to wrap your head around. So please let me know if I mess anything up. Please tell me if I can correct anything. Thank you for watching. I'll post more videos like this in the future.